Hi, I'm Mrs. Rutchling. Welcome to Chapter 10, Bond Polarity and Molecular Polarity. As a review from last chapter, electronegativity is how strongly an atom will attract an electron. Recall that fluorine has the highest electronegativity and francine has the lowest, and the trend is down. We're going to be using these values to help us figure out what type of bonds we have. To determine if a bond is ionic or covalent, we look at the difference in electronegativity between atoms. If there's a small difference, or even zero, the electrons are more likely to be shared. The greater the difference, then eventually we get ionic bonding, where the electrons are transferred. We're going to be using some cutoff values, but those cutoff values are just arbitrary. It's really a continuum of ionic character. We're just talking about bonds now, so if we look at the bond between hydrogen and oxygen, the oxygen is more electronegative, so it holds more of the electrons around here. Remember our probability map. The shared electrons are more likely to be found near the oxygen than the hydrogen. If there are more electrons, there's a slight negative charge or a partial negative charge, and that is illustrated by this lowercase delta with a negative sign. The hydrogen has the smaller share of electrons, and it has a positive nucleus, so it has a partial positive. This isn't enough to completely remove the electron. We're not creating ions with a full charge, but we have an uneven sharing with a positive side by the hydrogen and a negative side by the oxygen. That's a dipole moment, the separation of the charge within the bond. We show the dipole moment with this arrow. If we have hydrogen and fluorine, fluorine is very electronegative. It pulls the electrons. We have a partial negative charge by the fluorine and a partial positive charge by the hydrogen. This dipole moment symbol points to the more negative, and you can remember that because it has a crossbar that looks like a positive side. If two elements have the same electronegativity, diatomic share the electrons evenly. Those are nonpolar covalent bonds. The bond has no dipole moment. The electrons don't spend time around one more than the other. They're evenly distributed. If there's a large electronegativity difference, the electron is completely transferred. Here, the electron from sodium goes to chloride, completely transferred, electrostatic. That's an ionic bond. In between, we have two nonmetals, and there's a difference in the electronegativities. The bond is called polar covalent. So we have two types of covalent bonds, nonpolar and polar. It's a continuum. You can think of it as, when is it dark outside? Is it when the street lights come on? When you have to use a light to see? Or is it in the late afternoon when it starts to get a little dark, dusk? So there's a continuum. And we have created these artificial cutoffs. If we look at the electronegativity difference between the two atoms, if the electronegativity difference is slight, from 0 to about 0.4, we say it is nonpolar covalent. Nonpolar covalent. If it's in between that 0.4 to 2, it has a dipole moment. It is polar covalent. If it is greater than that, it is ionic. You may see different values depending on your reference source. The values that you need to use on a test will be given. If we look at the bonding, ionic is a complete transfer. Polar covalent, unequal sharing. Notice that it's closer to the chlorine than it is to the hydrogen. Nonpolar is shared equally.